think everyone saw what I was going to speak about in the first slide already, like a few times. Anyways, hello, I'm Tushan, and this is my colleague Zach, and we work for an awesome company called Zappy, and we've been running all of our core applications in Kubernetes for almost a full year, and today we would just like to share our experience of moving these applications to Kubernetes and dive into some of the interesting problems that we've had to solve along the way. Sorry. Just to give a bit of a background on the company and our tech stack, Zappy is an automated market research platform, and currently we're running about 27 applications or services in Kubernetes in production. We've got somewhat a typical Rails setup where we have Rescue to handle our background jobs, Redis as our main key value store, and MySQL for our database backend. We also have something what we call Quattro, which is our in-house computational engine. It's built on top of a Python library called Pandas, and it basically is our main workforce to do all of our heavy lifting for computation. And all of these services, with the exception of MySQL, have been migrated to Kubernetes. So now I'm going to hand over to Zach, who's going to give a brief introduction into what Kubernetes is and why we chose it for Zappy.
Hey everyone. So I need to go over a bit of terminology first. I don't kind of know what the crowd is like in terms of what their level of understanding of Kubernetes is, but I'm sure a lot of you have heard of it. Some of you may be running it already. It's a container orchestration tool, and that's a fancy way of saying it's a way of having something run your container and ensure that it's always running. And there's a whole lot of features that go along with that, but that's the basic understanding of it. A pod is a Kubernetes concept, which is a composition of one or more containers that run in or share the same resources. So, for example, they share a network stack. So, if you have two containers running together, they can talk to each other over localhost. A node is just a normal server with a few extra bits to allow Kubernetes to control it, and it usually has the container runtime on there. So, Docker, for example. And your pods would be scheduled on those nodes. And a group of these together would be a cluster, and you can have at minimum one node, and you can run that on your local machine if you want to. So you get a lot of things for free when you run Kubernetes, when you move your application there, which is a reason why a lot of people want to move there, because there's a lot of free offerings, not free offerings, but like simple offerings that you can get up and running with like Google GKE, EKS now. So you get cluster and application scaling, self-healing, which sounds really magical, but it's just a partial implementation of readiness and liveness probes, which is a way of doing a health check against your application. And if that health check was to fail, depending on whether or not was a readiness or liveness, readiness, for example, would stop traffic from flowing to your container. So it would essentially pull out of the rotation. If your application was to fail liveness, it would attempt to restart that single instance. And this behavior of self-healing gives you the ability to run on less stable infrastructure below Kubernetes. So you can run on spot instances, which are cheaper, and they may not be there for the next. They may not be there in the next 5 minutes. So having that behavior allows you to leverage them. You get rolling deployments, which you can get 100% uptime with a rolling deployment, assuming your health checks and readiness and liveness probes are working in good order. Automatic bin packing. This is trying to fit as many containers in as least nodes as possible. Kubernetes will try and shuffle things around in order to use as little resources as possible, which is a nice benefit. Secrets management. It has service discovery via DNS, and you also have some load balancing internally. So I listed a bunch of nice things there, but in order to leverage them, you do need to do a bit of work. And we'd faced a lot of challenges, and a few things broke down when we first attempted to move some applications there. So obviously, the first thing you'll do is Dockerize the application. It's fairly simple to do this, but there's a lot of the 80-20% issue here, where 20% of the time you're going to be fixing a lot of weird side cases and issues that don't exist when you're running outside of a container, for example. Graceful termination of application workloads is required for something like scaling and deploying. We'd never really done scaling very well before, so this was kind of new to us. Scaling effectively and efficiently was something we had to figure out. And resource management kind of goes hand in hand with that, trying to see how much resources you actually need to give to each application is kind of becomes a bit of an art at the time. We had to rethink database migrations. We had issues with assets. If the assets are in the container or compiled and stored in the container, you run into issues where assets are missing if you deploy a new version and a request goes to the new version and you get an HTML page and then it's like it tries to request an asset that's on the new version of the application, but the request goes to an old version, then you end up with a 404. So and maintaining consistent developer workflow. So we had tools that existed before, and we wanted developers to still be productive and still do things in the same way that they did with our legacy applications and legacy environment. So we needed to kind of support them along. We didn't want them to have to learn Kubernetes if they didn't need to or if they didn't want to. I'm going to hand over now to Tushan to talk about how we run rescue in Kubernetes.
Thanks. So Zach's highlighted a lot of the challenges that we faced, and we're going to take two of those challenges and deep dive into them in this talk. But if you guys have questions along the lines of any of the other stuff he has mentioned, then feel free to come to us afterwards. So getting rescue to work that we expected to work in Kubernetes was quite a challenging task. We were presented with multiple new modes of failure that we've never experienced before, and we really needed to rethink and redesign how rescue worked for us. And the first thing that I'd like to talk about is worker managers. So this is something that Rescue had in common with Quattro, our computational engine. So in Quattro, we had something called start workers, which is basically a process that took on all the responsibilities that Rescue Pool would for Rescue. So these worker managers were basically responsible for keeping the desired state of the workforce, so ensuring that all the workers would complete all their jobs under all scenarios. So for example, if a worker hits an unexpected error and exits, the worker manager would spring up a new worker in its place to maintain the same worker count as you did and had defined in the beginning. It was quite evident, like early on, when we were moving to Kubernetes, that worker managers just didn't gel well with Kubernetes, since Kubernetes already has, self-managing of state and managing the number of workers in your cluster. So also having a pool of workers in a single Kubernetes pod really contradicts the Kubernetes scaling model. So this is because having a lower granularity in the sense of having a single worker in a single pod is much more effective when you're trying to scale up and down rather than scale up a group of workers. Another problem that we ran into, particularly with Rescue Pool, is that there are different exit modes of a worker manager. So for Rescue Pool, they support a variety of different exit modes. These exit modes impact the decisions and the actions that the worker manager is going to take when it receives an exit signal. So previously in our previous stack, we were using a SIG-term signal, which basically meant that the worker manager would exit immediately, but then allow the workers to finish a job and then they would exit. So this leads up to what is called the Docker PID1 problem. In Unix-based systems, there's a process called the init process, and that's given the PID1. So any parent in Unix that doesn't have any process that doesn't have a parent is automatically adopted by the init process. And since Rescue has a parent-child structure, as you can see on the left, it means that if a child worker is busy doing a job and the parent process is killed, in the Unix world, the child worker would just continue finishing its job and be adopted by the init process. But in Docker, the main process is given a PID1, and it doesn't have the properties of an init process. Furthermore, Kubernetes judges whether or not its pod is running by checking the status of PID1. So it will immediately evict a pod if it determines that the PID1 is not running. So in our example here, if you were to send an exit signal to the rescue parent and a child is busy doing a job, there's no way for the child worker to perform any cleanup or to finish. It will just get killed abruptly. So our solution to this was to use a small lightweight process called Tini. And basically, it assumes the role of a Unix init process, but also at the same time, it delegates all signals between the Tini process to the rescue parent. So this way, when the rescue parent exits, the child worker is still allowed to complete its job by attaching itself to the Tini process. And once Tini has no more child processes, itself will exit and Kubernetes will terminate the pod. So what I've mentioned in the previous slide, where exit signals are sent to the rescue parent, is kind of like a typical scenario during a deployment where you're rolling out new code. Old workers are terminated, and then new workers with new code is brought up. However, in Kubernetes, we saw that in the Kubernetes world, there are a couple more modes of failures that you wouldn't get typically, because Kubernetes tries its best to protect the health of the cluster at all given time. So every single pod in the cluster is given a resource limit that you define. And when these resource limits are breached, Kubernetes will take action and kill the offending process in the pod. So in a case where you have a rescue pod with a limit of 5 gigabytes of RAM and the child worker exceeds that, Kubernetes will send a kill signal to the child worker. I'll be referring to this as pod level evictions. On a higher level, if a group of pods on a single node exceed the node's capacity, Kubernetes will start evicting and killing pods to protect the node. I'll be referring to these as node level evictions. So having the Tini process will get you to a place where the workers are able to complete a job during a deployment. But in reality, you may need to account for jobs that take 5 seconds, 10 minutes, or in Zappy's case, sometimes we have background jobs that take up to 8 hours. So how do you handle that during a deployment for Kubernetes in the Kubernetes context? So we need to think about reasonable timeouts. And timeout in our context means the amount of time between setting a shutdown signal to a process and then forcibly shutting it down when it doesn't respond within a time. So making sure that deploys and workers behave like how you expect, there's a couple of timeout hierarchies that you need to be aware of, mainly the rescue and the Kubernetes timeout hierarchy. It's kind of like an onion with multiple layers, and you want every single timeout that you set to be in some order such that no signals overstep each other. So in this example here, you wouldn't want your deploy timeout, which is the progress deadline seconds in Kubernetes. You wouldn't want that value to be lower than your rescue timeout because it contradicts how much time you think you're giving rescue to complete its job. So if rescue was in the middle of a job and you say, I'm going to give you 5 minutes, but then your deploy timeout is 3 minutes, it's going to cut it out at 3 minutes. And the reason why this is important is because a lot of these values have defaults, and sometimes they're not applicable to your application context, and you'd rather be explicit and set them yourselves to not get surprised. Case 2, pod level eviction. So this is typically when a worker uses more memory than it is allowed, such as on a pod level, and Kubernetes decides to shut down a worker. Thankfully, Rescue supports this with an on-failure hook, which basically allows us to execute some code or perform some cleanup tasks if a child is killed. So at Zappy, we have cases where the same job can sometimes use under 5 gigabytes of RAM, but then at certain extreme cases, under certain scenarios, it can use up to 30 gigabytes of RAM. And it doesn't really make sense to just simply requeue the same job in the same way after it was killed prematurely, because there's a very low chance that it's going to succeed the second time around. But at the same time, we don't want to upscale every single node in our cluster just to handle this one 30 gigabyte or 50 gigabyte edge case, because it's going to dramatically increase the cost of our cluster. So our solution, if you can see in the code there, is basically we have provisioned a supernode, which was just labeled a supernode, but it has double the amount of resources of all the other nodes. And during a failure retry, you see we override the queue which the job gets put onto, and we're allowed to redirect all of these high memory profile jobs onto the supernode. This is what works for us. It may not work in all scenarios. What do I mean by that? It's important to only select idempotent jobs, which means that if a job is altering the state of a database, for example, it could be incorrect that simply rerunning the same job the second time is going to yield the same result as if you just ran the job the first time. That's because you don't know what the job was doing when it was killed. It could have been halfway through something. So it's important to only attach via this extend from the module that we defined in the previous slide to selected jobs that you know are safe to retry. And the final case I wanted to talk about is node level eviction. So this is where the resources used by all pods on a single node exceed the capability of the node itself, and Kubernetes steps in and starts evicting pods to protect the node. And in essence, this is kind of our worst case scenario because no shutdown signal is sent to the parent or the child. So how do you recover from this? Fortunately, we discovered that all the sources of truth that rescue needs is stored in Redis. And you can see in this slide, I've defined a requeue job, which leverages rescue's backend. And you can actually look up all the workers that have been killed by looking at their expired heartbeats. And you can also retrieve the job payload, which is stored in Redis, which is basically everything that a worker needs in order to complete a job. So you can recreate these kill jobs, and you can see there we recreated onto the super queue again. So for us at Zappy, we have a scheduled job in the background that looks up Redis and polls for these workers with expired heartbeats and re-queues them if necessary. These kind of failure modes that I've described summarizes our main pain points that we've had with moving rescue to Kubernetes and making sure that it's production ready. I'm going to hand over to Zach, who's going to speak about how to scale rescue workers effectively and other components of our stack with metrics.
So something that we really wanted before we moved to Kubernetes was ability to auto-scale, to scale up and down. The primary reason was we wanted to optimize for cost. We wanted to scale up if we had a lot of load, a lot of HTTP requests, or a lot of jobs to complete. But we didn't want to pay for the fixed cost of having 20 instances at all times. We wanted to scale back down to 3 if we could. So that's why we wanted it. And to implement it in Kubernetes is actually pretty simple. Kubernetes has a component called the horizontal pod autoscaler, and it basically scales a deployment that you have based on an observed metric. And the default, or the main one that is used in most cases, is scaling on CPU. It also has support for scaling on custom metrics, which we'll get to in a bit. And this is powered by a component called metric server. This component isn't usually going to be available on all installations of Kubernetes, but it's fairly simple to add in after the fact. Its main purpose is to gather the metrics of each of the applications that you're running, in this case CPU, and aggregate that and provide that via an API to the horizontal pod autoscaler in order for it to query it every 30 seconds to determine what it should do next. Should it scale up? Should it scale back down? Scaling on CPU is pretty good for most workloads, and it's definitely easy to configure. Adding metric server, like I said, is very simple, but it is kind of challenging to perfect. Being able to find or strike a balance between scaling up too much or too little, or scaling up too late, or too early are found to be quite tricky. You have a few variables to tweak, which is the target value, for example. This is a more concrete example of an implementation of HPA, scaling on CPU. Over here we have the target value of the CPU. That's what we want to achieve. We want to, and that's an average across all of our application pods. We want to maintain 80% or lower CPU. If we breach that, like in this case, we're at 100%, we want the autoscaler to add more resources or pods and bring that average back down and into check. So tweaking that value is a bit tricky. There is another value that it interacts with, which is the requests. But if you want more detail on that, I can give that to you later. This is an example of an application that was actually scaling on CPU. It's mostly well behaved. The yellow line on the left is the target CPU utilization. And as it breaches and dips, you can see the replicas or the number of pods on the left-hand side going up and down in kind of unison almost. But it's not all great. It's good enough for most things, but there are some places where you'll get tripped up. And two of these examples are if there's a lack of increase in CPU. We found that in Rails, this sometimes when you have some blocking calls, you have some database hits that are taking quite long, you have some APIs that are just really slow downstream, and you can't efficiently use that CPU, so you're kind of stuck in a position where you can't scale to handle it in order to handle those extra requests that you're getting, even though you're already trying to do that via CPU. You need something else. Also, surge in the number of jobs. CPU doesn't quite map very well to an increase of like 1,000 jobs in the queue. You may have 3 pods that are currently working on a job each every 10 seconds. That doesn't quite translate to the fact that there's still another 997 jobs in the queue, and there's kind of no way to indicate that via CPU. So ideally, we want some context-specific metric. This is an example of scaling on CPU going pretty bad. The request queue on the top is HTTP request queue. As you can see, there's 2,000 requests in the queue, so we can't serve any requests at this point, so the user's browser is hanging. And the CPU is not reaching the target utilization. So we're essentially in a deadlock over here where someone has to go and manually scale up that application or figure out what the blocking calls are. So the solution to this is scaling on custom metrics, which I mentioned earlier. The horizontal pod autoscaler can actually utilize a custom metric. And you can scale on any metric that you can expose. You can scale on the temperature, which would be useless, but you can scale on anything. So Rails and Rescue, we've got some metrics that we like to use. For Rails, requests per second. How many requests can a pod handle on its own? How many requests are in the queue overall? For Rescue, how many jobs are in the queue? Or a processing ratio, which can be a custom metric, in this case defined as a ratio of the number of jobs in the queue to the number of workers available to service that queue. So unfortunately, custom metrics is not as easy to implement as just scaling on CPU. There are a few bits and pieces that are required. And I'm going to go through each of them in a bit of detail, but the HPA needs a way to get hold of the metrics that you're trying to expose. And there's a few bits in the pipeline that need to be put in place. So starting at the source, you want to expose some metrics from your application. You need something called an exporter. This is just a way of giving metrics or exposing metrics for scraping. It could be an endpoint on your application on an API. It could just be something sitting on the side that pokes at another service. Maybe it pokes at another set of metrics that you aggregate together and you come up with another value. But it's essentially some endpoint that returns a standard format of some metrics. Some examples that we use, a passenger exporter and rescue exporter. These are ones that we're currently using. We've forked these from some people who generously provided them, and we needed to make some tweaks to them. So we currently use the app request queue for passenger, and for rescue using the number of jobs in the queue. So now that we've got some metrics exposed, we need a way of collecting them, and we call this scraping. Specifically, we use Prometheus to do this. It's an open source alerting and monitoring tool, which in this case is the primary thing that we use to actually gather those metrics, and then we create Prometheus to get them again. So it's a pull-based metric collector as opposed to push, which InfluxDB, if you're familiar with, would be a push-based one. Prometheus discovers which services or applications to gather metrics from based on some annotations that you define on your pods in Kubernetes. Once it knows where that service lies, it will store it somewhere, and every minute on a regular interval, it will query those endpoints and gather those metrics up. So you now have the metrics in Prometheus, but you still have the horizontal pod autoscaler, which doesn't quite know how to talk to Prometheus. It's not well versed in that query language. So you need something in between. And in this case, we have something called custom metrics adapter. This is basically a message broker between the two. It's not magic. You still need to define what the query will look like that will end up resulting based on what the HPA is attempting to, what metric the HPA is attempting to fetch. And this is it's a bit complex, but the idea here is there's a series query, which is a query against Prometheus, and you give it a name, and this name is used in your definition of your autoscaler configuration. So this is where we finally configure our HPA to scale on our custom metric. Continuing with the trend, we're using the rescue jobs in queue metric. Plug that in, and we will then be scaling on our custom metric. It's going to be, it will behave, another thing to mention is the target value. We're targeting one job in the queue. So as soon as we breach that value, if we get 100 jobs in the queue, we want the horizontal pod autoscaler to schedule more pods in order to satisfy and bring that value back down to somewhere near 1 or at 1 ideally. So I'm going to show a quick video demo of just some scaling in action. Yeah. So it's pretty slow, so I'm just going to kind of skip through it. So on the top, we have the number of jobs in the queue. On the bottom left, this is the number of rescue pods currently scheduled and running. And on the right, we have the number of nodes in the Kubernetes cluster. So we've kind of plateaued on the top there and coming back down now. We will scale up a bit more on the rescue pods in a bit, and a bit later you'll see that we'll scale up one node actually. So I'm just going to skip ahead. And I think, yeah, we've scaled up on one node on the right-hand side there. And after a couple of minutes, it'll scale back down. I just didn't have enough patience to wait for it. So, yeah, and yeah, I didn't have any editing software, so sorry about that. All right, handing over back to Tushan to discuss some more important things that we couldn't get to.
Cool. So I think we're a bit out of time, but I just want to quickly gloss over Redis. It was a very core component of our Rails stack, and Redis availability is pretty much the same as application uptime for us. And those are a couple of points that we needed to address. And just to gloss over some quick wins that Kubernetes got for us, the main thing was reducing costs, even though we increased the number of applications by 10x. So what Kubernetes allowed us to do was to duplicate our entire production cluster into Sandbox, and every single team got their own team cluster. But because of the scaling and how Kubernetes packs these pods, not all the apps are used all the time. Not all teams are operating on it all the time. They have it available, but we were able to do that. And a few others, I suppose. Cool. Questions? So I think the first time we deployed Kubernetes to a sandbox environment to when we finally got into production was about a year and a half, or slightly less than that. Yeah, so I mean, it was operating fine on sandbox in order for teams to work with, but it wasn't production ready. Yeah.
So I'll start from the end there. So it's very dependent on your application. You have to monitor your application for a few days and see what usage it gets. That we had to do that for every application. You put some metrics around it, gather metrics. We have at the moment InfluxDB and Telegraph, which it's actually pretty simple to hook up to Kubernetes and gather all the CPU usage and memory usage of each of the pods. So I would say you spend some time looking at what they're doing and then adjust and make sure that it's adjusted to what you're expecting.
So I think Tiny overdone in it because it's more lightweight. We originally used
something on that. Tiny is actually built into Docker now, so it seems to be the way that they're wanting to go. They're doing the same thing. We didn't really care. We actually started using. We did start using the Kubernetes actually, but then Tiny came along and it was apparently a little bit better, so we used that. And our Tiny's built into Docker, but we haven't actually switched over to it yet. So we do have a separate front end as well, but we still do have applications that do require assets to be kind of compiled and shipped with the Rails deployment. The solution to the problem that I mentioned is actually to move your assets onto a CDN. Because as soon as you put all your assets inside the container, that's kind of the source of truth. So you'll have two different versions of assets running at any one point in time. So the way to get rid of that problem is to move the source of truth outside of the deployment kind of area and have it. And obviously, fingerprinting of the assets is important so that you always get the latest asset.
Cool. Thank you very much.